Hello friends, today we will see cascade amplifier, or you can say this two-stage op amp, two-stage op amp. So we will do AC analysis. We will find pole and zeros. Okay, so in cascading, say we have two amplifiers. Gain is A1 and it has some output resistance, then cap, say R1, C1, then another amplifier, gain A2 and R2, C2. Okay, so in this case we have two amplifier, and this is input voltage, this is output voltage. So this two amplifier consists of two poles, one by R1 C1 and one by R2 C2, two poles. So this is two pole system. So there are two amplifier. We can say it like as a two-stage amplifier as well. Now, so say omega 1 equals to this, omega 2 equals to this. So if we draw a Bode plot for this amplifier, then it will be something like this. So this is omega 1, this is omega 2, and this is omega, this is A1, A2 in dB. Okay, now in this case it consists of two poles. So this is its phase diagram, and this is 0, 90, 180 degree. Okay, so now we have in previous video we have seen that for stability purpose phase margin should greater than 45 degree. Okay, but in this case our phase change is 180 degree, so here we don't have any margin, so system is unstable. Okay, now for this for stability purpose, what we can do, either we move this omega 2 outside UGB and omega 1 towards origin. So this is one way. Another way is we put here somewhere over omega 2 we will put some 0, so that there is a pole 0 cancellation. Now let's see how to create a 0. So let's see how to create a 0 and how we can move pole 2 how we can move omega 2 outside UGB and omega 1 towards origin. So moving omega 1 towards origin and omega 2 outside UGB, this concept is known as pole splitting, and this we will do using Miller compensation or using Miller effect. So we will put one cap here known as compensation cap. This is A2, this is A1. Now, so now what it will do, say this is C1, this is C2. What it will do, it will basically increase cap at VO1 and reduce resistance at output. Okay, now let's see how. So this is Miller cap, so we know it will change. This is R1, this is C1, and here cap will be A to C, C, C. Okay, A2 and R, and this will be C2 and here C, C. So we have applied here Miller effect, and what it has done now, our omega 1 equals to 1 by R1 C1 plus A2 CC. Okay, so our omega 1 frequency reduced, moved towards origin. Now in this case you can say that it is going to increase cap, so it is also going towards origin, but it is not the case. If I write omega 2 1 by R2 C2 plus CC, so this is actually wrong, because here output resistance is changed actually. Now let's see how. Now consider amplifier as a transconductor. Okay, so this is say its transconductance GM. Okay, and if we are taking here this Miller cap CC, and here I am taking C1. Okay, now I need to find out R out here. So this we can reduce something like this. So this is some beta factor, this is GM. In previous videos we have seen how to find out output resistance for this kind of structure. So our R out is given by 1 by GM beta. Okay, so R out is 1 by GM beta. Now beta is basically CC by C1 plus CC. Okay, so this is our R out. So our omega 2 become 1 by 1 GM beta into C2 plus CC. So GM beta C2 plus CC. So this is our omega 2. Basically output resistance is reduced here in this case. Now output resistance is reduced, omega 2 will move to higher frequency. Okay, so now here GM is basically so this concept is known as pole splitting. So omega 1 moves towards origin, omega 2 moves towards UGB or outside UGB. Okay, so both poles moves far apart from each other. Okay, previously R out is 1 by R out, and R out value is very high, that's why omega 2 is near to omega 1. Okay, so this is concept of pole splitting. In next video we will see how 0 is created in this, and we will understand this 0. Regarding this 0 is right hand plane 0. We will see that 0. Okay, thank you.